Chairperson of the Technical Session Number 3, Dr. Perera, Professor Jonathan Binns from Australia, lecturers, distinguished guests, heads of departments, esteemed researchers and participants. On behalf of the Department of Mechanical Engineering, I extend my warmest welcome to the Chairperson of the 3rd Technical Session of the Conference, a pioneer in automotive engineering and mechanical engineering in Sri Lanka, Dr. Perera. He was the Director General of Tertiary and Vocational Education Commission of Sri Lanka. Afterwards, Dr. Perera joined as the Project Director of Science and Technology of Human Resource Development Project and AATD supported project in Sri Lanka. Currently, he is serving as a senior lecturer at the Department of Mechanical Engineering at the Open University of Sri Lanka. It is with great pleasure and excitement that we gather here today to embark on this intellectual session dedicated to shaping a more resilient future through innovative mechanical engineering solutions. Therefore, this conference serves as a dynamic platform for researchers to explore novel avenues in mechanical engineering that enables us to enhance resilience across domains. Now, I invite the Chairperson, Dr. Perera, and the authors to be headed. It's time to commence the session. Dr. Perera, the floor is yours.
Thank you very much, Saman, for the introduction, one of my students. And I'm very indeed honored to be here with you, and nice to see the large gathering who are interested in mechanical engineering, representing foreign universities and the industry and the university. I hope that this session will bring enormous benefits to the students and the staff and also the industry in Sri Lanka. This is the 16th International Research Conference of the Surgeon Athukorala University. The theme of the conference is Achieving Resilience through Digitalization, Sustainability and Sectoral Transformation. The theme of today's technical session is Achieving Resilience through Novel Mechanical Engineering Solutions. And I think this is a very good time to step taken by the university and the department. Today's session consists of 5 technical papers presented by authors, mainly from the Gunawardhana University. We have them on the table. Before we begin, let me announce the rules of the presentation. You have been given 12 minutes for the presentation, and the audience can clarify during the Q&A session. You are given 3 minutes for each presentation. I cordially request all the members who are present in the audience to actively engage in the Q&A session and also limit your questions relating only to the topic presented. Also, may I request all the members to put your mobile phones to the silent mode, not to disturb the presenters and the session. And with that remark, let me invite the first research paper titled Numerical Analysis of a 3D Wing with with an active flow control method authored by KNS Perera, MM Basnayake, and SLMD Rangajeeva. The presenting author is KNS Perera. KNS Perera is an aeronautical engineering graduate from the Department of Aeronautical Engineering of Faculty of Engineering of Sir John Athukorala Defence University, Sri Lanka. Currently he is serving as at Sri Lanka Air Force as a flying officer. He was awarded trophy for best student in aeronautical engineering at Sir John Athukorala at General Convocation of KU in November 2022. Over to KNS Perera, flying officer.
Thank you for the nice introduction, sir. Chairperson, the senior lecturers and lecturers, good afternoon you all. Today our presentation, our research is based on design of an active flow control method and its numerical analysis. The outline is shown on the slide. Basically, there are two types of flow control. The one is the passive. It is based on changing of geometry, and the examples of passive flow control is the vortex generators and slats, and there are many more modern discovered passive flow control methods. When it comes to active flow control, it is about adding an energy to flow and then by controlling the flow over the surface, so that it makes it possible to make a smooth maneuvering, and also for the commercial aircraft to be more fuel efficient by removing the existing steering parts that create drag. There are many types of flow control methods. The synthetic actuators are known as open loop, and it has zero net mass flux method, that is the in and out mass flow rate is same. The flow jet arrays, it is the method that we were concerning of. It use of continuous flowing as suction, and it consists of microcompressors. This research was based on analyzing the aerodynamic characteristics at unstable angle of attack, and therefore we focus on obtaining data for our research, that is in detail for the wing. The wing chooses the aerobatic aircraft. Then we selected the VT6 aircraft. It is in the Sri Lanka Air Force fleet. It is currently used for the aerobatic and fighter conversion training. There are three main objectives in our research. The first one is to select a location, an appropriate location for apply this suction and blowing, and the next primary objective was to implement the suction and blowing profiles in order to carry out the CFD simulation, and finally to assess the effectiveness in application of suction and blowing. There are four main sections in our methodology. First one is the solid modeling, that is involving modeling of the original wing and the modified wing. Then the mesh generation, then CFD analysis, and finally the post-processing. For the active flow control method, the initial idea was generated by studying the principle of synthetic actuators. Basically, it's a dual phase suction and blowing. In this research, we had converted into a single phase suction and blowing, that is, we placed one slot to suck the air, and then that air will be blowing from the another slot. And finally, it satisfies the law of continuity. For the inclusion of slots, we had to refer many literatures, and we found several literatures by Shah that's involving the effectiveness of the slot wings and the location. Therefore, we obtained those data from that research, and in order to match the location of slots, we had to analyze the point of flow separation. Then we carried out the simulation for the same details that are given in the literature, and then we found that the mean point of flow separation was similar, that is 0.81 times the mode length, and therefore we directly imported those sort locations and converted into our research according to our mode length. For the modeling, we obtained the data from the original 86 aircraft technical specification manual, and we obtained the coordinates for the generation of airport from the Lanka LC software, and we used SolidWorks in order to build this solid model. The purpose of modeling of slot surfaces, rather than keeping as pores, is to define custom boundary conditions in order to implement the suction and blowing. Net generation, we use two utilities. The dimensions of the domain mesh is given in the table, and we use snappy hex mesh usually to make an appropriate mesh, including the wing. And we have to apply many refining regions in order to keep our I plus below 10. But we also have to give an attention on the size of the mesh. For the CFD analysis, we use the mean cruising velocities and cruising altitude of the BT6 aircraft, and we use K omega SST so that it can solve the near bound region as well as the free stream. For the turbulent parameters, we use an online calculator to calculate to obtain those parameters. And nearly 58,000 calculations we had to carry out in order to make the results convergent. There were three designs. The first design was included the suction, one suction slot at the leading edge and two blowing slots near the trailing edge. The result was not much as expected, so we had to restrict our simulations up to 3 angle of attack. Then we had to redesign it by adding more slots. That is, we had two suction slots at the leading edge and 3 blowing slots at the trailing edge. The results was drastically changed in this design. As you can see in the graph, at lower and up to the middle angle of attack shows an higher increment, but the latter part is not as much as we expected. So we came to the conclusion that during at high angle of attack, the point of flow separation moved towards the leading edge, so that the flushing at the trailing edge is not efficient due to this high wake turbulence. Then we had to intervene this suction and blowing, so that the blowing can sweep out the flow separator and retarding the point of flow separation, moving towards the leading edge. And while the suction slot will accelerate the dead air that is wake over the nearby region, making and continuous flow. Also, we had to observe it from a glide mode so that we can ensure that the weather is it happening as we are expected. In the post-processing of the design 3, it shows drastically higher increment in aerodynamic efficiencies at low as well as higher angle of attack, and it shows the desired efficient characteristics of an active flow control method. This graph shows the lift percentage gain and the drag percentage gain and loss when compared to the design 2 and design 3. The aerodynamic efficiency percentage gain comparison with of design 3 and design 2, you can see at low angle of attack it shows almost similar increments, but when it goes to the high angle of attack, the aerodynamic efficiencies are much greater, so that it again satisfies the desired characteristics. Further, we had some limitations. The main limitation was the computational cost. For the mesh size of 3.9 dB, it took about 27 days, so we had to stick into a gauze mesh so that it will limit our simulation for one simulation it takes 10 days. This is a comparison which has taken from simulation that carried out at 12 degrees of angle of attack. On the right corner you can see that uniform and low pressure distributions over design tree when you compare to the original wing. And on the left corner you can see the way region is swept out more in design 3 compared to that of design 2 and the original wing. About the future work, it is required to design a proper mechanism for opening and closing of slots because we cannot keep it open because it produces more drag. And also we need to carry out an stress analysis. Further, we need to validate those results using a mean time. In conclusion, our model of active flow control system is a combination of suction and blowing, and the implementation of suction and blowing safety analysis, we use the custom boundary conditions, and it was an effective method to implement this suction and blowing. Further, each design has proved that there is an effect on the aerodynamic efficiencies, and design 3, which consists of blowing and leading edge and suction and trailing edge, is the most effective active flow control design to apply for an aerobatic aircraft. Finally, we would like to thank the academic and non-academic staff of the Department of Aeronautical Engineering at KU for giving us a continuous support to finalize this research. And these are our references. And this is the end of my presentation. And thank you for careful listening.
Thank you very much for the interesting presentation. Any questions from the audience?
I have read the results, it is 5.0 per meter. What is the difference?
Sorry, sir, what is the table?
The table one, where you have got the specification of the wheel. This span is given as 10.1 meter.
So in that table, it is not included in the presentation. It is the total span of the wing that is
Both sides?
both sides.
Ah. So both sides. Now, how do you practically implement this loading and such?
So we need to include the micro compressors for the both sides. Or otherwise, we need to apply a separate compartment to provide this air supply. But basically, these co-flow jets are consistent and micro compressors. They are calling the micro compressor arrays.
Those should be operated automatically.
With an electrical power.
Electrical power. But how do you actually find out when to operate, when to suck and when to blow?
So it's based on the type of operation. If for a conventional operation rather than aerobatics, then it needful of this system is not much needful because it is more designed to prevent this flow separation, that is, prevent stalling and undesirable angle of attack the aerobatic aircraft can undo. So, for the conventional aircraft operating at normal manuals, is not required.
And then during working, how do you actually incorporate the suction and blowing? During working, during pilot working?
So, I think
during working, how do you incorporate the suction and blowing?
the velocities.
Yeah, those points, how do we incorporate to the model function and during simulation, modeling and simulation?
That means the number of slots. So
Yeah.
that's where as we go back to the simulation. So this design one included only one substrate and two blocking structure. For the results, we gave us very less. That means you can see the blue color line shows middle range of angle of attack is very less than the original one. So that means according to the wingspan and the wing surface area, the required energy that's applied that from these individual slots is not enough. So that's the reason we had to go for another design.
Yeah. Nice presentation. I have two questions. Question one is, what are the available or current state of the art of active flow control measures taken in the found in the literature or you have experience?
Sir, this is still in research level. That is, it has not conventionally applied to any other of the aircraft. But the companies such as Boeing, they are implementing these to the engine pylon. That means it disturbs in engine pylon, it disturbs the air that comes to the surface of the wing. That from the active flow control method, they are trying to make the flow continuous rather than disturbing from the engine pylons.
Right, that gives another question. Now, blowing and suction of air in different places need some mechanical or rather equipment to be mounted inside the wings, right? So that may add weight, additional mass to the in your simulation. Have you considered those elements as well?
No, so we only consider the behavior of the flow in the research.
Okay. Okay, my original second question, now third question. Slide number 24. Slide number 24, can you, the graph with the design 2 and 3, this is design 1 was having issue, then you made another 2 design and simulated. Now, can you explain the blue and red again with around the angle of attack around there 6?
Yes, sir. Design 3 is that interchange blowing and suction. At the lower angle of attack, both of designs gave similar aerodynamic efficiencies, but when it goes to the higher angle of attack, it shows less. Our expectation was to have higher greater efficiency, aerodynamic efficiencies at lower as well as higher angle of attack. So that's the reason we select design 3 as more efficient when it compares to design 2. The red one.
Any reason for the red and blue to vary between 6 degrees? That as you see, what could be the reason?
Yes, at higher angle of attack due to the this is the reason that we go when to design 3. That is because in design 2 we kept the blowing at trailing edge. That means the flushing that can be done by the blowing is not enough at high angle of attack. That means the flow separation is moved towards the leading edge. So that the energy is not enough. So if we can prevent that the point of flow separation coming towards the leading edge, then this can be prevented. So that's why we interchange the blowing and suction. We took blowing near the leading edge so that we can flush the point of flow separation before we overpass the leading edge. So that's why we have designed this.
Okay, thank you.
Thank you.
have done the simulation only. How are you going to practically do it? Is there a possibility of trying it physically on the aircraft or something? Do you think it is possible to try and get some result?
Yes, sir. It is incorporated with micro data arrays, sir. Before that, we need to do an stress analysis. That means providing changing the original design can affect the stress analysis, stress flow into surface. So that before we are going to implement, we need to do it and proper stress analysis throughout the week. Then, sir, we need to design a mechanical approach to the opening and closing of these slots, because we done simulation by keeping the slots open. That means without providing any suction and blowing, we just keep the slots open and we did the simulation. You can see in the right side the lift has drastically decreased and the drag has increased. That means we cannot keep these slots open, so that we need to design and mechanism, proper mechanism to the opening and closing slots.
So, proper mechanism is designed, it can be done.
Yes.
Thank you.
Thank you very much, audience, for constructive, the reviewers' point of view questions. These questions will shape up your research in future. We develop the research. I have a small question, even though we are running here. You have done this study for Nanchan CJ6. So where do you fit into the national agenda? Is there a plan Sri Lanka to develop a local plane with the performance?
Right, it's the same 86 aircraft. Maintain CJ660, there are named version. The export version is 86, that is CJ68. And we currently have 86 aircraft for the aerobatic and fighter conversion training. So, and in past period, we had one go some incidents regarding this aircraft. By implementing, after going through all these field research work, we could have a possibility, we might have a possibility to prevent these further unfavorable situations.
Thank you very much. Our next research is based on the development of low-cost energy harvesting flow tile that operates from food stage. Authored by W.R. Fernando, A.M. Abhishek, Lieutenant Commander PMKC Chandimal. The research is being presented by W.R. Fernando. Mr. Fernando is currently a temporary instructor in the Department of Mechanical Engineering, Faculty of Engineering of General Research on Kurukulaarachchi Defense University, Athukorala, Sri Lanka. He is a graduate from the same university, BSc Honours, Mechanical Engineering, first class degree. He is a past student of Vidura College, Colombo, and St. Thomas's College, Mount India. His research interests are machine design, material science, solid modeling, and finite element analysis. Over to you, Mr. Fernando.
Very good afternoon to you all. I am Mr. Fernando and I will be presenting on development of a low-cost energy harvesting flow tile that operates on food streams. For a brief introduction, the energy crisis is a problem faced by many countries in the world and currently Sri Lanka as well due to dependence on non-renewable sources. So, as a solution, solar and wind energy plants are now being implemented. And another source of renewable energy available is the kinetic energy available in the human food streams. So, the concept of energy harvesting flow tiles is relatively new, and the available models in the market are being costly when it comes to Sri Lankan countries. So, if we can model a low-cost model, and we are able to generate power locally at scale aim of this project was to develop a low-cost flow tile that can generate power from footsteps, and the objectives were to design and fabricate a low-cost energy harvesting flow tile which can harvest kinetic energy in human footsteps, and to test and optimize the energy harvesting capability of the design tile. In order to achieve that end, we implement this methodology. Firstly, the problem identification, next literature review, developing conceptual design, detailed design calculations, fabrication, testing, documentation, and final report. From literature, we were able to find out that about 2 to 20 watts of power is available in a single step of a human when walking. And the energy harnessing methods are as follows. And after surveying the literature, we were able to use the rack and pinion mechanism to generate the power and using electromagnetic generators. The available models in the market are as follows, and the final company mentioned here, KPCS, is the leading manufacturer of power generating flow tiles, and the price of one tile can go up to $160. So this is the conceptual design we proposed in the initial stages of the design, and we were able to go forward with it. This includes a flexible top layer, and below that is an intermediate layer. So this intermediate layer consists of 4 triangle-shaped tiles, so triangle-shaped layers, which are hinged to the side of this tile. So the vertical motion is converted to rotational motion through the rack and pinion, and the alternating rotation of the input shaft is converted to one-way using the two-way to one-way rotational converter. For the material selection of gears, we utilized a multi-criteria decision-making technique. Initially, the performance indices were developed, and then we showed the effect of the developed performance indices in the decision-making process. And finally, using the electric method, we solved the MCDM problem. These were the materials we considered for the production of the gears, and through the solving the MCDM problem, we were able to select carbide steel as the most optimum material for this project. For the motor generator, we selected the stepper motor rather than DC motor because the stepper motor produces a large induced voltage even at low rotational speeds, and the selected module was NEMA 20. These are the considerations we did when making the design. The average mass of a person to be 75 kilograms, average stride length to be 0.16 meters, and the average time per stride to be 0.1 seconds. The downward displacement we considered was 10 millimeters, and the downward velocity calculated was around 0.1 meters per second, and this is the tangential velocity of the sphere. So after that, we did all the stress calculations for components, and then we went on with the solid modeling. And this is the isometric view of our design, and we carried out finite element analysis as well. So this is the final product. To your left side, you can see the final product, and to the right side, you can see the tile without the top part. So you can see the intermediate layers that are out of the. For the electrical circuitry, we made use of 2 ampere bridge rectifiers. Since the stepper motor, when we use it as a generator, it produces current in two phases. And we made use of a 1 millifarad standard capacitor for the smoothing. During the fabrication process, we made some changes in order to reduce manufacturing cost and time, and considering the economic prices we had encountered in that period as well. So instead of a spur gear, the input shaft diameter was increased to 20 millimeters and was splined to meet the requirement. And we made use of already available bevel gears rather than the design ones. And the output shaft diameter had also been increased from 10 millimeters to 20 millimeters due to the changes in bevel gears. And we had used wood for the tile housing. These is the fabricated components without the electrical circuitry. So here you can see the tile without the top cover, and here you can see the intermediate layers which are used on the side of the tile, and tile cover with the top cover as well. So for the elaborate testing and optimizing, we vary the die spring compression for in 10 millimeters, 20 millimeters and 30 millimeters, and we made use of 3 smoothing capacitors, and we testing with 2 stepper motors, NEMA 17 and NEMA 23. So these are the results we got using the NEMA 17 stepper motor, and the maximum voltage was around 13 to 15 volts, and the maximum amperage was around 0.2 amperes with the use of 30 millimeter spring compression and 1 millifarad capacitor. These are the results using NEMA 23 stepper motor. So here we were able to generate around 17 to 23 volts and 0.7 amperes using a 1 millifarad capacitor and a 30 millimeter spring compression. So this is a small video of the working of this tile. So here you can see the alternate motion of the input shaft is converted to next we carried out field testing. The model was made using the NEMA 23 stepper motor, 30 mm downward deflection instead of 10 mm, and a 1 millifarad capacitor. So the model was tested using a RAM with a participation of 4 candidates, and the voltage readings had been taken, and each candidate was then interviewed about their experience on this tile. So these are a small video on myself testing this tile, and here you can see the generated voltage in the model. So these are the voltage readings we got in the field testing, and an average of 18 volts were produced during this testing. So these are some of the comments made by the candidates. Felt afraid the first time, not that much of a problem the second attempt. No discomfort when stepping on the center, uncomfortable when stepping towards the side. Afraid to step on it, felt uncomfortable, put a sign to inform people before they step on it. Moving on to the cost power calculation, the average power generated from this tile is around 12.6 watts. And the total cost per model is around, and the total cost per watt for the model is around $18 per watt. And the estimated cost per watt for the prototype is around $22.50 per watt. Moving on to discussion, the unique additions in the design compared to other models can be summarized as follows: inclusion of an intermediate layer, inclusion of a two-way one-way rotational converter, and inclusion of a stepper. After lab testing, the downward displacement was increased from 10 mm to 30 mm. From the field testing phase, it was observed that the power generated by the footstep depends highly on the speed of walking, mental preparation for the downward deflection of the foot, curiosity to step on it, mental state on comfortability, type of footwear, enthusiasm for the concept of power generating flow tile. As conclusion, the design, fabricating and testing outcomes of a low-cost energy housing flow tile that operates from footsteps have been proposed in this project. This utilizes a rack and pinion to convert the vertical motion to rotational motion, which then goes through a two-way one-way rotational motion converter mechanism using bevel gears, ratchet and balls, and is fed to the stepper motor, which acts as a generator. The cost per watt comparison of the available model with the available models in the market are as follows, and you can see that our model gives a relatively low cost per watt value. Hence, we can say that the aim of this project, which was to develop the low-cost flow tile that can generate power from footsteps, and the objectives which were to design and fabricate low-cost energy harvesting flow tile which can harvest kinetic energy from footsteps, and test and optimize the energy harvesting capability of the design tile has been successful. As future works, we would like to propose a cascade connection with battery management system, and the inclusion of a gear ratio for the 2A200 canoe. These are our references. Finally, I will thank Lieutenant Commander PMKC Chandimal and Mr. KPCS who are both former lecturers of the Department of Mechanical Engineering, Faculty of Engineering, General Sir John Bogahawatte University, and the head of the department and the academic staff of the Department of Mechanical Engineering, Faculty of Engineering, General Sir John Bogahawatte University, for the supervision, guidance, and constant monitoring throughout the course of the study. Thank you.
Thank you very much for the interesting presentation. Questions from the audience?
Thanks very much for an interesting presentation, and it's amazing that you've got some real topics coming out of this thing. But you mentioned earlier you had some piezoelectric option. Did you mention why you didn't go with the piezoelectric option?
Piezoelectric, there are models which uses these piezoelectric materials, but the durability and the longevity of these products are very good. So, and the power generated is also very small. So, if I can.
So it could almost be a non-moving part.
Yeah.
So that is so small.
Sorry?
That'd be affecting such a small amount. It might almost be like non-moving parts.
Yeah, but so here you can see the PCT ceramic and the sustainable flow. Sorry, the sound power and the PCT ceramic. Those are both using piezoelectric materials, and you can see that the power generated is around 0.1 watt per second and 8.4 milliwatt per second. So the power generated is very low when compared to the electromagnetic generators.
Thanks.
Right, thank you very much for the nice presentation. Interesting, and there are so many application of harnessing pressure converted to electricity, and especially as the previous question, the piezoelectric, that also because when it comes to ergonomics and safety, when you got what is the maximum variation of 10 to 30 millimeters is a deflection.
We initially went with 10 millimeters, but since we got higher results with the improvement of the deflection, we went with 30 millimeters.
Yeah, if you go to 3 centimeters, then there may be utilization issues of that particular tile. Have you done any studies on that, or the customer perception on tile that is going down when you are working?
Yes, sir. For this, we mainly focused on the designing of these components and the power generator. So, when we did the field testing, we found out that there are certain non-technical aspects as well. So, regarding the comfortability and the mental state of those people who step on these tiles. So, usually when we make, let's say, a pathway from these tiles, we should display a sign that says that this is a path that generates flow tiles and generate electricity, and there's a small reflection when you walk on it. So there are those aspects as well we have to consider. And during the lab testing, we went with 3 different spring compression rates, 10 millimeters, 20 millimeters, and 30 millimeters, and we finally went with 30 millimeters. But when we are applying this, we can change those deflections and make this product more user-friendly.
But in this scale, what is your per step voltage? Your device?
Our model,
Yeah.
our model around 12.6 volts.
12, about 12 volts. Now, when you see the cross section or what is the mechanism, now there is a rack.
Yes.
And there are 3 bevel gears. And one bevel gear is both ways it is driving the motor, right, or the generator. And there are about then 1, 2, 3 to 4 interfaces in gear linkages. Have you calculated the energy loss during this transmission versus any energy loss calculations?
There is some energy loss, but we were able to overcome it using the rotational kernel. So, if I can do so here, you can see that even the step is over, the output shaft is still rotating. So we were able to reduce some of the losses as well during the inclusion of this 2800 rotation kernel. And the shaft and the input shaft is rotating both ways.
Rather than recovering losses, you are adding more losses, but you are trying to recover more energy from the return stroke. Right, so that is okay. That's all. Thank you very much.
Normally, explain to you how it goes here. You would have really estimated the loss of energy or otherwise transmission efficiency. And think about more simplified transmission mechanism like this to get the power generated. And also this your time is a flexible time. It's like a suburban.
The top layer is we use the rubber, but the intermediate layer is a rigid layer, but it is hinged to the side of the tire builder. So when someone steps on it, it caves in rather than we get a sudden drop.
This cost you estimated based on your model or otherwise for a large
for the model, but this is the dimensions are quite similar. The dimensions will change, but the materials will change.
Now, I will think about large area. Your cost per watt will not come down.
So if you meters, we can generate more power, but in this mechanism, in this single dial, the power won't change.
Yeah, my question is a little bit different from what Dr.
Thank you very much. A very good presentation, and you have done a lot of research work. It's good people are thinking of renewable energy. My question is now what you show here. This mechanism and the earlier picture showing on the slide 26. 26. Most of the calculation, right? Now, this mechanism is for one time. It's for one time. So now say if you have a footpath of 2 feet by 10 feet footpath as we've shown, you have to have series of these. So you have to consider the cost of each section that you are going to build compared to the time you that's it. We can't put a normal tile that we have a tile, otherwise normal tile can crack, But having, you should have done a calculation and shown to the audience what is the energy generated and what is the cost saving happen for a walkway. These are mainly designed for walkways, not sort of place like this, where people walkway generate energy. Have you thought of that? Can you tell us the audience how much will be the cost?
Yes, sir. We only designed a single tile for this project, and the applications of this can be applications can vary. So here we can use it as a single tile, say in an entrance or at a gymnasium. If you are this can be used in gymnasiums as well for exercises, and we can generate power from those as well. So if you have to calculate those kind of energy, to study on the amount of people who are, say it's a walking park, how many people utilize go through this park in a given day at a given time. So, and with the walking speeds and the mental state as well regarding the comfortability. So all of them comes into account when we do a total energy output analysis. So in order to do that, we need more time and resources.
Okay, so extend your research work and do a calculation and then keep going. Thank you very much.
My question is regarding in the long run, when you use the materials you have already used. So, what is the concern when it comes to moisture and corrosion attacks? Will that be an issue and your cost saving? Have you studied for the tiles that were much expensive, what they have used to as a solution for maybe this problem?
So can you read the last one?
Yeah, moisture contamination and corrosion in the long run, and the tiles that you showed in the comparison, whether they have given a solution for that at a higher cost when it comes to the long run.
So when it comes to corrosion, so we proposed cowrized steel. So these steels are very durable, and we can with this lubrication, so we can go on with that. And the tile we can seal after connecting, after assembling the components and after putting the top layer as well, we can seal it. So using that we can give a solution for the corrosion and moisture as well. And when we look at the other companies, only Asian has given the solution, like only they have given a robust tile which can be implemented in outdoors as well. So other companies, I haven't seen them giving solutions for those.
Thank you very much. I think this research has to go a long way and will go a long way. Thank you.
Thanks.
And marine engineer propulsion and workshop during the Chandimal in Sri Lanka. Over to you, Lieutenant Commander Priyashan.
Thank you, sir. Good afternoon, everyone. The study was conducted by Captain D.S. Bogahawatte, Commander K. Kurukulaarachchi, Lieutenant Commander LAKR Athukorala, and myself on empirical feasibility study to design, build rigid hull inflatable boat for special operation units in Sri Lanka Navy. In this video, you can witness a high-stake maritime operation known as Visit Boat Search and Seize (VBSS), skillfully executed by the Navy. The centerpiece of this mission is none other than the rigid hull inflatable boat we call RIB, a versatile and indispensable vessel renowned for its agility and adaptability in the risky waters of the open sea. The United States Navy donates to SLMD. Those boats have been in use but are now approaching the end of their life cycle. Unfortunately, due to the foreign currency crisis faced by the government of Sri Lanka, SLMD is unable to purchase new boats, and there are no immediate prospect of receiving RIBS donation from other countries. However, the United Nations Office for Drugs and Crime (UNODC) has indicated that may be willing to fund the project to Sri Lanka Navy if the Sri Lanka Navy can design and build the RIB themselves. So we conducted a study to see if it is possible to design and build a reef needed for special operation units within the Sri Lanka Navy. The main question we aimed to answer was, how can we understand and address the crucial factors that determine the successful creation of a low-cost reef according to the requirement of the Navy's special operation units and all within the capabilities of NBBY. We have covered our research under the following objective. First, to estimate the reef's total hull resistance at the customer specified maximum speed. Second, to estimate the total propulsive power and select the propulsion power package the boat decides to achieve the maximum speed. Third, to optimize the reef dimensional parameters, the center of weight to improve the performance and stability. And last, to determine the fulfillment of intact stability criteria of the design. Our research methodology has focused on these areas. The reef is designed with solid single rigid hull and a flexible inflatable tube. It operates compatibly up to sea state 3 and can operate and survive in sea state 3. Total length of 7.5 meters and the beam of 3.0 meters admission. And it can carry up to 12 people operating at a range of 50 nautical miles at a maximum speed of 35 knots. And as per the customer's request, that means the Special Operation Unit of Sri Lanka Navy, the propulsor is a stern drive. And we developed a 3D hull model in Rhinoceros 3D software following a comprehensive weight estimation considering all boat's components, and we determined the center of gravity. Utilizing the hull shape and the new center of gravity, we calculate the initial draft and the trim angle in Orca 3D software. Subsequently, we use NavCat software for the calculation of hull resistance and the propulsion analysis. We calculated the total hull resistance under three conditions, that are light running condition, most probable for design running condition, and the heavy running condition for enable understanding of design performance. Since this craft goes as high speed, to understand the hydrostatic and hydrodynamic forces contribution, we studied the float number as indicated in this slide. In this slide, you can see a simplified ship's drive rate highlighting the efficiency. So the stern drive propelled boat typically achieve approximately 50% propulsion efficiency. So we use this value for the analysis, calculating efficiency as thrust horsepower divided by the brake horsepower, which is 355 horsepower for our system. To reach 35 knots of speed, this will require around 350 horsepower in light running condition. We evaluated engine propeller interaction for maximum speed and performance even with the hull deteriorate condition. The key factors include ensuring the engine can deliver the full power under conditions, effective propulsion in various scenarios, and optimize fuel consumption. Sea trials confirm that the stern drive efficiency, confirming its suitability as the reef's propulsion system while addressing these considerations. To optimize the boat's performance, variable like speed, displacement, length, beam, dead rights angle and LCG are crucial. For our rig, the speed is fixed because it's the customer requirement. We selected the dead rights angle between 17 and 20 based on our experience. Balancing speed and comfort. Scaling the boat by 1.2 and 1.5 factors relieve that the effective horsepower requirement increased by 22% and 37%. Thus, the current size struck the best performance on balance. The intact stability crucial for the small boat safety. We assess it as per the IMO intact stability code guideline, ensuring the rig's ability to resist capsizing. The standard curve is shown in this slide. So now we will discuss the result we have gained from this study. We transferred the 3D hull design created using the Rhinoceros 3D software into NavCAD software. We opted the Swatsky method as it was deemed the most appropriate for the predicting resistance and the interaction between hull and the propulsion. This choice was based on the compatibility of the input data as outlined table indicated in this slide. The total hull resistance developed using NavCAD software for light running condition is shown in this figure. This figure shows the total effective power estimation for the light running condition. We estimated hull resistance as shown in this table for the above narrated hull condition. For our proposed rig, the NavCAD software returned a remarkable hull efficiency score of 0.98. With this value in hand, we could calculate the light running condition. The thrust horsepower stand approximately 177.5 horsepower. This achievement marks the successful completion of our first objective. As a result, we constructed a power curve for our light running condition as illustrated in this figure. It serves as a crucial assurance that propulsion system operates effectively under the conditions where it is operating near its design limits or handling of design scenarios, all while staying with the operation prescribed limit. The fuel efficiency was found to be reasonable as per the detail indicated in the shown table. After search in international market, we found the Mercury diesel power Western Drive Model 4.2 to be the ideal choice within 350 horsepower output at 3,800 RPM and inline diesel configuration, and it fulfills our requirement. This achievement marks the completion of our second objective. Initially, the LCG was at 2.7 meters from the transom of our rig design. We used NavCAD software to assess different LCG options. After analysis, we choose 2.9 meters as the optimal LCG, achieving the third objective of our study. The G-set curve developed by the Orca 3D software is shown in this figure. Using the 3D hull in Orca 3D, we created a static stability curve compared to IMO standards. The table in this slide confirms the craft meet all the stability criteria, marking the achievement of our fourth objective. This slide shows a summary of all assumptions and validity of the same on completion of the project. In summary, we determined that the Mercury diesel Bravo Model 4.2 is the optimal choice for our rig. with total hull resistance of 7.1 kN in light running condition. The rig performs well in sea state 2 and can handle in sea state 3. We selected 20-degree tension dead rise for the ideal speed comfort balance. Its dimensions are 7.34 meters in length and 2.7 meters in beam, carrying 12 passengers up to 55 nautical miles at a speed of 34 knots. In our next paper, we will discuss about the reef's IRC structure design, and we will explore its maneuverability characteristics and delve into crucial aspects such as manufacturing cost and life cycle management. These are the references we have used for our study. In this video, you can witness a reef, similar kind of reefs which we have designed and built in our naval boat building at Basnayake.
Inflatable boats is a lightweight construction with high performance, improved stability with a solid ship-powered flexible tube and gun. The design is stable and seaworthy up to sea state 3. The boat can be used as a rescue craft, safety boat or dive boat. Its shallow draft, high maneuverability, speed and retrievability to safety boat damage and low steam collisions are advantages in this application. Draft can achieve a maximum speed of 30 knots.
Thank you.
Thank you very much for the presentation. Question from the audience?
Thank you very much for your presentation. I have questions. They calculate the resistance without electric circuit.
Yes.
From the software.
Yes.
Can you go to the graph that shows the power and the resistance and the speed? The other one, this is the full load condition. I consider you show. Yeah. Now, what was the plane speed and plane of the boat? You observe it? Planing speed?
Planing speed at about 15 knots.
15 knots. Right, that is clear from this. But I have doubt that the gradient of the curve before plane is very sharp, very high, because you find only the internal resistance. You take the reading, no? You have taken 3 points at about 6 knots and then about 9 knots, yeah, about 12, right? No? Yeah. I mean, gradient of the curve is increasing resistance with the speed seems to be high. That is what my observation. Anyway. Have you built this one or just only one?
Recently we are building one boat at Inflatable.
Right. And the dead rise angle you mentioned about 20 degrees. Is that the midship dead rise or transit? Transit.
Yes.
But actually dead rise variation is very important along the length of it for the plane. I mean, just not only the transfer dead rise, but how it varies from bow to stern, and that is most important. And how it varies from midship to stern also very important to make the boat plane early. It can be also by, if you run the program with different dead drives variations, because you can 3D model any shape, and then you will see with the dead drive variation how the hull shape become actually more important when it comes to the plane speed. And also to reduce the resistance that you may observe. And I think in your paper you mentioned that there is no any towing tank in Sri Lanka, but there is a towing tank in Perera University. Right? Yeah, there is one. But the only thing that has no all facilities to measure the resistance. You have a tank is there, and the carriage is there. But the only thing, if you can fix actually measuring arrangement with the load sets and etc., then you can do the measurement. Because about 10 years back, with the Ocean University student, I did the actually towing tank test, model test. And with the model test, you can actually come to a very accurate estimation. So actually, the Savaski method used Perera results. I think it is plus or minus 5% line. But if you want to do a model test, you can do it at Perera. That's all.
Dead right angle, generally we take the dead right angle at the transom and as well as certain points up to 0.7 of the longitudinal length overboard, and we include all these details as well to refine the product as well, sir. And what was the other one? Dead right angles, and also sir, dead right angle we worked out from 70 to 22, and we realized that 19.8 is the best thing. Very yes, 70 to 22 and 19.8 for construction purpose. We took it finalized at 20 degree at transom. Thereafter, gradient we took it what was given in the software. Mid-drive would be much larger than that, maybe 35. 20, yes, 27, yes. Mid.
Thanks very much, and yeah, certainly in Australia we like to try to build as many boats as we can in the country as well, so it's not just we can't get them now. Getting a sovereign capability on shore is a massive advantage, I think, in any sort of naval construction program. But no, thanks very much for your talk. The length overall and the beam overall, did you optimise those or are they sort of set, and how would they go with any sort of launch and recovery operations that you're thinking of? The length overall and the beam overall. Did you optimise them on? Yes, sir. Yeah. Have you considered how that would go with the launch and recovery operations? Or have you considered launching it yet off a control boat, for example?
I will answer, sir. Initially we started with 7.5. And can you go to the last slide? Yeah, that one. No, please. Yeah, so fourth one, we started with LCG of 2.7, but we need to have it 2.9 gave the optimum value, and thereafter we overall length also we started at 7.5, and we altered, we initially went for the length ratios, and we improved 1.2%, increased 0.8%, but the effective horsepower is increasing. But when you increase the length, only the length increasement, we gain certain thing. But the problem was when we increasing the length, the planing speed was increasing. So we want to run at a longer speed, then it comes up generate the dynamic forces. So that was the issue. So when you increasing the length, we are getting better performance. but the planing effect is not good. So we stick with the 7.34 overall length and LCG of 2.9. Another consideration was now if you go like that, it will get plain, but the slamming, the profounding effect is so high, but we can't do the mission operations. So then there was another problem, profounding is so high, so then we retracted back a little bit.
Thanks very much. And I think that slamming question is perhaps the next thing to tackle, because that tends to drive up the dead rise angle enormously, which then might increase the resistance in terms of my feedback. So it's a real trade-off there once you start looking at slamming. But thanks very much.
Thank you very much, audience, for constructive questions. And thank you, Priyashan.
Thank you, sir.
Our next research paper is based on development of a doubt dividing machine with counting ability for local bakeries in Sri Lanka, authored by KPCS Kalavitigoda, Gunawardhana, Vidura, Captain is Bogahawatte, FBYR Silva. Presenting author is KPCS Kalavitigoda. She is currently a temporary demonstrator in the Department of Mechanical Engineering at General Surgeon for the University of Sri Lanka. She completed her BSc Honours in Mechanical Engineering from AATD and is awaiting her graduation in October 2023. Please welcome Ms. Kalavitigoda.
Thank you, sir, for that kind welcome. Good afternoon, everyone. My final year research project was on the development of a door dividing machine for local bakeries in Sri Lanka that has counting ability. So, bakeries in Sri Lanka actually have the process of door dividing done manually, while the rest of the world uses a machine and is much more faster. But in Sri Lanka, while this process is done manually, it is very time consuming, labor intensive, as well as quite inefficient. So these machines, these door dividing machines, are not manufactured in Sri Lanka, but if they're needed, they're actually imported from countries like India, China, and Italy. But if they're imported into this country, with the added shipping cost and tax, the prices are actually 2 or 3 times higher than the original price. So the aim of our project was to develop a cost-effective door dividing machine that has accounting ability as a novelty approach to automate the process for the local bakeries in Sri Lanka. And in order to do this, our objectives were to design the components in the door dividing machine, to develop a mechanism to count the door balls, to fabricate, test and optimize the model, as well as to find the ideal speed to operate the rounding mechanism. So we carried out a literature review on existing door dividing machines, and most of the systems that are present have electric, hydraulic or pneumatic systems to operate the cutting mechanism. And the type of door divider that should be used depends on the effort required by the door dividing machine and the type of door that's used. So the door dividing machine works with food, and for machines that work with food, the material that has to be used is stainless steel. So in this case, stainless steel is mainly 3 types, grade 303, 304 and 316. So in our machine, when the actual machine is produced, we propose the use of stainless steel grade 304 since there is no acidic compounds to use grade 303. And in order to push the dough forward to be cut, there are many mechanisms such as rotary extrusion, piston ram, a knife, pocket, and stress-free dividers. While in our project, we used double screw extruders to push the dough forward to be cut. And how this machine works is that there's mainly common two types, press cutters that are door divider machines and pneumatic or motor control dividers. So the press cutters actually have the dough ball and it's made into a circle and put in a tray. And using a circular shaped cutter, the circular shaped dough is cut into little pieces and the tray is rapidly moved to create the round, small dough ball shapes. While in the pneumatic motor control dividers, the dough is actually placed into a hopper and the dough is pushed forward through the extruder to be cut from a blade. Now, for our methodology, we first reviewed the literature, then we carried out review on the machines that are actually present and the components that you have. And we created a conceptual design. And then we carried out calculations to find the dimensions for the gears, shafts, the couplings that were used, and the chain and sprockets. Then we selected the materials for those components and we designed the model through SolidWorks and carried out finite element analysis. Then, once we ensured that the components were safe under loading, we went on to the fabrication process and testing and optimization. So this was the fabrication of the extruders. The rounding mechanism that we used, so our actual machine, we weren't able to produce it because of the current, because of the country's economic crisis while we were doing this project. So we had a 2/3 scaled down model. And for our rounding mechanism, we 3D printed the circular and the cover. And the material used was PLA. In order to turn the rounding mechanism, we had a motor and a light dimmer. So usually light dimmers work by varying the voltage given to a component. So we connected the light dimmer to the motor so that we were able to fulfill the last objective, which was to vary the speed of our rotating mechanism. And in order to count the door balls that were coming out of the rotating mechanism with the circular, we used an Arduino board, IR sensor, LCD display, and a battery. And we configured code into Arduino IDE so that we were able to count the number of door balls that left the exit. As you can see in the video, this was our final model. The extruders were inside and we had a chain and sprocket. We included gears, there was a gearbox inside. And the cut door balls would fall into the rounding mechanism, and once it exits, the IR sensor would detect the door balls and count it on the screen. So, in our results, one of our objectives was to vary the speed of the rotating mechanism. And so we varied the speed of that. And at 5 different speeds, so 50 RPM, 75 RPM, 100 RPM, 125 RPM, and 150 RPM, we found which speed produced the most ideal round-shaped dough ball. So we took the 5 speeds and we produced 20 dough balls from the same mixture, and they had the same weight. And from these results, we can see that the most ideal round-shaped dough balls were produced when the rounding mechanism plate was turning at 100 RPM. We carried out finite element analysis for the input shafts and the output shaft. So we were able to see that the minimum factor of safety was greater than 1 for all the shafts that we had used. And the maximum stresses that were produced in the shafts were lesser than the yield strengths of the materials. This is also carried out for the gear wheels. And we also carried out convergence for gears A. Although the values do not converge in this instance, the problem we had was that even though we wanted to decrease the element size below 1 millimeter, the computational power we had was not enough. But if we were able to decrease it more, the values would eventually converge. So some of the problems that we encountered was finding a suitable motor for the application. We actually used a Viper motor because that was one of the motors that could handle the high torque that we had in the machine. And the difficulty in finding that was because of the unavailability of the components in the market in that day. We also had an idea to incorporate an elbow mechanism, but eventually, while we carried out the testing process, we found it that the vibrations from the machine would not let the elbow mechanism function correctly. So as future work, when we're making this actual machine at full scale, we would want the machine components that come into contact with the door to be made of stainless steel grade 304 or 316. And instead of using a motor to rotate the rounding plate, we can directly use a bevel gear system so that we can reduce the cost of having two motors in the machine. These are our references, and we'd like to thank Captain D.S. Bogahawatte, Mr. FBYR Silva, and Mr. Singha, who are supervisors for this project, and all the academic staff of Mechanical Engineering Department as well as Marine Engineering of KDU. Thank you.
Thank you very much for the presentation. Questions from the audience?
Thanks for another very interesting talk, and obviously, necessity certainly is the parent of invention and innovation here. You used a 3D printing for the actual mechanism?
Yes, for the rounding mechanism.
Yeah, do you have an idea how you could actually construct that out of stainless steel? Or because obviously in 3D printing you can make any shape possible, but how would you make that out of stainless steel or quite got to that stage yet?
Well, that part is usually made out of some sort of hard plastic. We didn't actually we built a scaled down model, so we didn't actually go into using stainless steel for that part. We just used the 3D printer.
So you wouldn't need to make it out of stainless steel?
No, some of the machines that actually use that type of mechanism don't use stainless steel for that part. We found that from the literature reviews.
Okay. Thanks very much.
Yeah, nice and practical work. And what have you seen? What is the latest or the most modern technology on this door dividing and counting? The available machineries in the world, not in Sri Lanka, in the world that you have found?
So, when we looked at the machines available on the internet and the resources that we found, the machines didn't actually have a counting mechanism installed into the machine, so that was part of our innovation.
Why did you think of getting existing machine and installing the counting mechanism separately?
So we actually we went around to a lot of places in Sri Lanka to try and find a door dividing machine here, but we couldn't find it. So, and the limited details of the machine components and how they function on the internet, the information was limited. So some of the components that we included were of our own thinking rather than the actual components in that machine.
Okay, thank you very much. Nice presentation.
Thank you very much for the presentation. Did you take about no weight from everything? Weight or the weight is machine?
So the machine?
No. Once you prepare the dough, did you take the weight of it? It's varying or it's being constant?
So we had a scaled down model, so the dough balls that we produced were actually much more smaller than the dough that would be produced in an actual machine. So once we carried out the testing, we weighed the dough balls that we got, and they were roughly the same weight because we had the motor rotating at a constant speed.
It's a very good presentation, it's very good hard work you have done. It's a design of your own, or is it something you have searched from the internet?
So we looked at existing machines, but usually the components inside weren't available to discuss. So the outer appearance of the machines were what we actually had to work with. So we imagined, so if we wanted to move the dough forward, what kind of applications that we would use, and we just implemented our ideas.
Yeah. Now, what do you think? Do you think you can give this to a local bakery to find and see? And other thing is, I want to know what is the production rate? Because now all bakeries they may be making breads and various other things. This is just maybe the cutting mechanism. I know. So, how much loss you can make within an hour or something?
So the cutting speed of the extruders was 30 RPM. So per minute we would get 30 dough balls. But this was the scaled down model. We were planning to manufacture this for the bakery in KDU. But since there was no machine in this bakery, they only had the mixing. So our main aim was to build that machine and reduce the labor that was involved, because usually in a bakery there would be one person separating the dough balls, one person he would have to round it and weigh it. So that whole process would be automated with that machine. So the number of people employed in that section would be reduced and replaced by the machine.
Okay, but I think since you have done a prototype, get hold of one bakery and give it to them and try and see the feedback, so that will you can improve it further. Very good, thank you.
Thank you very much, audience, for questions. I have a small remark to make. I have seen many moving parts exposed, which you have to consider long run. We are going to commercialize this. And I would like to relook at your payback period calculation again. And also you have an extruder. It's very important that lubricants do not contaminate the dough in operation. Anyway, thank you very much for the presentation. Our last research paper is on the title of Automatic Clothesline Retrieval System for Domestic Purposes, authored by AATD Mantika, EMHD Bogahawatte, and Perera. The presenting author is Perera. Kevin is an electronic and telecommunication engineering undergraduate in the Department of Electrical, Electronic and Telecommunication at General Surgeon Athukorala University. And her email address is given in chapter number 3. Thank you.
Thank you for that kind introduction, sir. A very good afternoon, ladies and gentlemen. I am Kevin Perera, an undergraduate of KDU, and it's a privilege to stand here to present our topic on the automatic clothesline retrieval system for domestic purposes. Here is the outline of the presentation that we will be focusing on for today. So let me give you all a small introduction. I guess all of you have been there, especially during this rainy season, where you have to constantly think about unpredictable weather. I mean, it's pretty frustrating to keep your laundry outside, having it to soak under unpredictable rain. Now, indoor drying and laundry dryers come as alternatives, but they have their own set of drawbacks. For example, high cost, high consumption, high energy consumption, and fabric damage. So to address all of these problems, our system will develop by automating the drying process. So the primary objective of this product is to enhance the user experience, to provide a comfortable home and work experience for the users, so they don't have to attend their laundry matters. Also, one of the key problems that we aim to address is due to unpredictable rain, clothes will be in continuous contact with rain, so further getting damp. So the drying process has to go in cycles and cycles. Also, another thing is, how often do you all go back and forth to check if your whole cloth load is dried? So with our system, these concerns are mitigated as the drying process is automated. So you all don't have to go get constant checkups to do this. So we did a small literature survey to identify the existing research in this field and what sort of aspect that should be developed and the gaps that needs to be filled. So concisely speaking, many models use sensor integration systems such as LDRs and rain sensors. And those existing models use an existing system like a cloth rack, and they add more existing features like a motor to fold and hold or a roof to hold and hold. So by analyzing these literature results and to optimize the system, we developed an intelligent cloth system. So the scope of this project is primarily focused on the busy household families of Sri Lanka, particularly the ones who go to work in the morning and come back home late in the evening. So this is the main sensor integration of our system. So this uses 3 sensors: the rain sensor, the light sensor, and a dry moisture sensor. So the priority is given to the user. So the user needs to, depending on the requirement, the user can take the clothesline in or the clothesline out using a switch. So this program is in fact adopted as the clothesline is yet at shelter at night. And further, during daytime, when there is rain, the clothesline will come back inside to shelter and alert the users via an SMS alert. And when the whole cloth load is dried, the clothesline will also go straight inside, alerting the user that the cloth load is dried. So there are 3 inputs to the microcontroller: the rain sensor, LDR module, and from the moisture sensor. Also, we have the switch from the user as well as limit switches. And from the output, you get a GSM module giving alerts to the user, as well as a stepper motor and motor driver to control the back and forth motion of the cloth rack. So we designed some sensor tests for the rain sensor and the LDR sensor. So basically, the rain sensor has a 5x4 sensing pad, and when the water droplets get in contact with the sensing pad, this will decrease the resistance and the output voltage will be further decreased. So depending on the average of the results we got, we measured our threshold voltage as 2.3 volts. So the rain sensor will trigger at that point by 0.1 milliliters of water. For the LDR test, we kept, in a sunny day, we kept the LDR and got the average wattages. So we decided to take the threshold as 2 states, as 1 and 0. So during the 0 period, meaning from 8 a.m. to 6 p.m., it will be outside, meaning on the sun, and at night from 6 p.m. to 8 a.m. in the morning, this will be inside the shelter. So one of the unique features of this system is this dry moisture sensor. So we had to make our own circuit and a sensor material as well. So what we do here is, this sensor comprises of 2 metal clips, and the cloth should be attached to that metal clip. So based on an assumption, we decided that the cloth that should be clipped from the whole cloth load should be the highest time to dry. And this is also clipped in a concise area of that cloth, so that place should be also the final part of the dry process. So what happens here is, the cloth acts as a switch. So if the cloth is wet, there is a full current going through that part. So the output from the operational amplifier will be a higher value, a positive higher value. So when the cloth gets dried continuously and there won't be any current left, so at a point there won't be any current left, meaning it will be an open circuit. So then the output of the operational amplifier will be a negative value. So depending on the positive and negative values, we decided to retreat the clothesline in when there is no current going through the circuit. So we scaled down our model and from 30 to 30 centimeter dimensions, so using a linear railguide methodology. And what we did here was, we used a railguide, and using a stepper motor, this will rotate the railguide and in turn carry out the cloth track. As you can see the frame here, it will carry out in and forth from shelter to the sun. So we designed this sensor by basically upon assumption. So this sensor, the dry moisture sensor, can be only put to one cloth depending on the assumption that it's the cloth which takes the most time to dry, as well as it's only just one place, so that place also needs to take the most time to dry. Also, this is a pre-installed and customizable model, so depending on the user requirement and depending on the housing proportions for the user, this can be installed, so it lacks portability and doesn't not very much adapted to different setups. So we have managed to design an intelligent system that provides a clothesline which automatically retrieves the clothes in shelter in the events of rain, at night, and when the whole cloth load is dried. And also furthermore, it will give real-time updates to users using an SMS. So these are some snapshots of our final product, the scaled-down version. So this model has more potential to grow. So for additional features, we can use a weight sensor that can calculate the weight to prevent overloading and to prevent the limit that is exceeded. Also, this sensor, which is a dry moisture sensor, can be modified further to mitigate the limitations that I mentioned. To further increase the accuracy of the system, a humidity sensor can be used as well. As of conclusion, this intelligent system, due to time-saving automation, will give the users what it needs, and also this will promote eco-friendliness, and also it will promote home automation advancements as well. So these are the references I used. At last, we would like to extend our sincere thanks to Professor Rohan Lucas from the Department of Electrical and Electronics for his invaluable oversight and for the help for this research paper. Thank you very much.
Thank you very much. Questions from the audience?
Right, nice and practical application again. Now you said when it is raining, it will be retracted into a shelter.
Yes, sir.
And what will happen after that?
So when
so the rain stops, now it will go back.
So when the rain stops, so the rain comes in contact with the sensing pad, that means the rain sensor, right? So after that, it needs to fully evaporate for the clothesline to take back to the sun again.
Yeah, the logic is clear, the mechanism is not clear. How it goes and comes back. So what do
you mean the mechanical part?
Yeah, mechanism, how it works, how it moves.
So we use a linear railgun basically. That model is mostly used in 3D printers where you use a rail and then using these bearings it will go in and forth between the movable part.
Okay, a screw gun kind of thing.
Yes.
Right. Okay, now what is the state of the art now? Can't you buy these things off the shelf?
Yeah, so basically in Sri Lanka, nothing is automated in this aspect. So we have, basically cloth racks and people will put cloth lines and stuff like that, but nothing is automated. But in case of the world, there are automated systems. But the novelty here is the moisture sensor where it can detect the wetness or the dryness of the cloth. But in some of the applications, they have used time as an assumption. So they measure the time that where the whole cloth load is selected. So in that case, it's like that.
Okay, now addition of the sensor to the moisture sensor to one fabric, and you mean the assumption that is the last dry.
Yes.
Okay, that's all. Thank you.
What length of the clothesline you can use?
So for our model, we used 2 bars in parallel, that is for 30 centimeters.
What is the length of it?
30 centimeters.
30 centimeters. Now, practically, when you want to implement it in practice.
So basically, as I mentioned before, this is like a customizable model. So depending on the user requirement, this changes. So it can be scaled up to like 5 times of the actual scaled down version, probably.
5 times?
Yes.
So depending on that, how many cloth you can make?
So up to, so the scaled down version is for like 60 to 70 grams of clothes. So if it's for the actual implementation, we were hoping for 5 kilograms.
5 kilograms.
Yes.
Okay, thank you.
Thank you, sir.
It's a very good design that you have thought. It's mainly for the housewife.
Thank you, sir.
One day you become a housewife or working wife, it should be useful. There are some extreme conditions, but this is alright for when the weather is calm and everything, so your sensors are there, you measure the intensity of the sun, and then when the rain comes it will move. But with the current weather conditions, at times we have very windy conditions, like cyclone, then the rain comes at one direction. Have you thought what could be done in such situation? Is this going to work, or what is your opinion on that?
So we can use a humidity sensor and a temperature sensor. So beforehand, now in this model, rain has to drop for this model to work. So if you use a humidity or a temperature sensor beforehand, we can identify the threshold values and keep it inside shelter at lower cases.
In your design, have you described how many number of cloths that you can lay at one time, or is it only designed for a particular type of clothing, or not all types?
Yeah, so we tested the dry moisture sensor using for the cloth which takes the most time to dry. So we used a cotton wool handkerchief So depending on the material, it actually depends. So if you're using a cloth load, which maybe consists of like a towel or something like that, that's the most one to drive. So that's in case a limitation in this, because it's based on assumptions.
Okay, thank you.
Thank you, sir.
Thank you very much, audience. There's another session starting at 3:30 the same venue, so we have to rush. Any other concluding remark from the audience? Because we have another Q&A session according to the agenda. You can spend a little more time if you want. Looks like no questions. So let me thank again the audience, distinguished panel, and the constructive question session, which will shape up this research future. This was very informative and showcased the caliber of the students of KTU and the staff. And I would like to wish all the very best to all the presenting authors and co-authors, and request to further this research. And finally, I would like to thank for the management of the KTU for inviting for this session. Thank you.
Thank you, sir. Also, I would like to thank the authors for the insightful presentations. Now, it's time to award the recognition and the tokens of appreciation, and especially to the dedication and hard work shown by the authors. To award the certificates, I kindly invite the Chairperson, Dr. Rasika Perera, on stage, accompanied by the Head of Department of Mechanical Engineering, Captain D.S. Bogahawatte. First up, we have Flying Officer KNS Perera. Mr. W.R.U. Fernando. Lieutenant Commander AATD Priyashan. Miss KPCS Kalavitigoda. Miss K.N. Perera. Thank you, Dr. Perera. For your presence today was a great honor for us. Sir, I kindly invite you to remain on stage. Now it's time to express our sincere thanks to our chairperson of the third technical session of the International Research Conference for the year 2023. Dr. Rasika Perera, please accept our token of appreciation. Thank you, sir. Now it's time to express our sincere thanks to the judge panel for their collective efforts in selecting the best research paper for the International Research Conference of KDU 2023. I would like to invite the Head of Department of Mechanical Engineering, Captain V.S. Bogahawatte, once again to hand over the tokens of appreciation to the judge panel. First up, we have Dr. J.R. Gamage. Dr. W.K. Vidura. Engineer Lal Veerasinghe. Thank you, dear sir. So, as we reach the pinnacle of the event today, the judges are calculating the results and they'll let us know shortly. Thank you. Thank you, sir. It is evident that this prestigious conference had brought innovative advance of mechanical engineering into the spotlight. Also, a special note to the authors, you are invited to publish your valuable research work in Journal of Advances of Engineering and published by the Faculty of Engineering of KDU. Also, once again, I would like to thank our judge panel, Dr. J.R. Gamage, Dr. W.K. Vidura, and Engineer Lal Veerasinghe for doing an outstanding job in finding the best research paper. I would like to thank each and every one of you for being present with us today at the third technical session of the International Research Conference for the year 2023, session number 3, and spending your valuable time to participate. That marks the end of the third technical session for the year 2023. I hope you enjoy the refreshments afterwards and have a pleasant evening. Thank you.